Welcome to today's Explainer. We're about to embark on a seriously incredible journey right into the heart of high-energy physics. We are going to uncover a startling physical realization that's been hiding in plain sight, buried inside massive amounts of raw CERN collision data. We'll be looking closely at how a specific Python script completely flips the script on how we view subatomic particle tracks, transforming just, well, abstract numbers into a vivid picture of cosmic fluid dynamics. Get ready because the results we're breaking down today are absolutely explosive. So imagine the ultimate needle in a haystack scenario. When you're dealing with the colossal data outputs of the CERN Atlas detectors, you're looking at millions of collision events and particle tracks. These are literally the fundamental building blocks of our reality. So how do you find the hidden geometry of the universe in a billion rows of data? It's a ticking clock mystery. The data is vast, it's chaotic, and it's incredibly dense. Finding the underlying truth requires a tool that doesn't just, summarize the data, but actually listens to what the physical universe is trying to tell us. And that brings us to our ultimate truth-telling tool, singular value decomposition, or SVD for short. Now, SVD doesn't play games with the numbers. Instead of guessing where friction or attenuation might occur and then just adding in these artificial fudge factors, SVD simply diagonalizes the stress field and lets the geometry reveal itself. It is entirely unbiased. Whatever structural relationships actually exist in that raw input data, this tensor maps them directly into phase space, keeping the physical integrity completely intact. Okay, let's dive into our first topic, Section 1, the flaw in Jess math. To really appreciate what SVD does, we have to understand the inherent flaw in standard statistical data analysis and why the usual way of doing things actually obscures the very physics we're trying to observe. Think about what we might call guess math. This is your standard processing. It uses things like z-scores and artificial scaling, literally forcing every single column of data into neat, tidy 0 to 1 ranges. And sure, it makes different units really easy to plot on a clean graph, but it completely destroys actual physical reality. Now, compare that to raw reality. This is what unfiltered cavitation SVD does. It processes raw pascals. It preserves the unscaled, violent physical pressure drops of the system exactly as they happen. To really ground this idea, just think about what scaling does to extreme physical forces. Standard processing literally pretends that a tiny 1 Pascal atmospheric flutter has the exact same statistical weight as a 100,000 Pascal ocean hydrostatic head. That's crazy, right? When you're looking at the violent, energetic extremes of particle collisions, normalizing these variables completely erases the actual physics. We absolutely need a mathematical engine that can handle violent pressure drops without smoothing off the edges. Which brings us to Section 2, the SVD engine unveiled. This leads perfectly into the tool we'll use to properly analyze this Atlas data. And guys, this isn't just standard data science. This is cavitation SVD. We're processing the raw state matrix of a fluid body experiencing localized phase rupture and pressure transients directly in raw pascals. Think of it like a fluid dynamics metaphor. Imagine a liquid cavitating. When the fluid pressure suddenly drops below the local vapor pressure, voids form and then violently collapse into high-magnitude pressure implosion spikes. This is exactly how we are going to model the subatomic world. All right, moving right along to Section 3, streaming the root files. So how do we actually unleash this engine on the data? Well, we run a dedicated Python script to sweep through 24 Atlas root files. Step by step, it's like watching a hacker at work. First, it targets the analysis T-tree within those files. Second, it automatically detects and bypasses empty zero-event grid output blocks, so we don't waste time crunching empty space. Third, it flattens out these jagged 60 muon Cartesian vectors, things like track angles and spatial coordinates, into continuous particle node state vectors. Finally, it calculates the pure scalar cavitation magnitude, which we call VCav. It streams all those adder products into a really compact 7x7 gram matrix to compute the global spectrum, basically without melting our computer's RAM. Now, when you run this, you can literally feel the energy in the room as the terminal spits out the live execution results. Out of the 24 root files located, the script successfully locked onto 5 active files and skipped a whopping 19 empty grid blocks. The dynamic vector alignment locked in at k equals 7. It streamed those unrolled particle tracks, computing the global eigendecomposition across an absolutely incredible 542,853 total collision events and 462,104 individual particle tracks. The raw matrix secrets were finally ready to be revealed. And that brings us to the big one, Section 4, the 99% discovery. Once the streaming completed, the script spat out the eigendecomposition results. And what it showed wasn't just interesting, it was a fundamental paradigm shift. One single mode completely dominated the entire spectrum. Just let this number sink in for a second. 99.104810%. That is the sheer magnitude of variance held by mode 1 alone. In this massively chaotic field of hundreds of thousands of subatomic tracks, almost all of the system's energy variance is bound up in a single primary physical behavior.
What's really fascinating here is exactly what's driving that 99%. The singular value for mode 1 is nearly 11 million, and the primary coupling is VCav. We are talking about pure scalar cavitation dominance. In fact, if you dig into the raw terminal separation ratios, you see a 14.4 times magnitude dominance over mode 2 and a staggering 277,000 times dominance over the directional angles at the very bottom. The directional vectors basically just vanish into statistical noise. The subatomic collision field is entirely dominated by total kinetic agitation energy density, not directional geometry.
Let's pull this all together. Section 5, subatomic fluid cavitation. This realization takes us completely out of the realm of abstract data and drops us directly into profound theoretical physics. Kinetic energy and momentum are the true drivers here. When we look at subatomic tracks through the lens of that massive 99.1% variance, they stop looking like tiny billiard balls randomly bouncing around on an XYZ axis. Instead, they behave exactly like cavitating fluids governed by pure kinetic scalar momentum. The energy density is what dominates the collision field entirely. So here is the absolute crucial takeaway. The invisible subatomic world operates as localized phase ruptures. Subatomic tracks are governed primarily by scalar momentum agitation, where the pressure drop is strictly proportional to our primary coupling, VCav squared. They are absolutely not governed by some arbitrary directional split along horizontal or vertical track angles. The universe, down at this fundamental scale, is a highly agitating, cavitating environment. The force mechanics at play here beautifully illustrate this reality. Whether we're looking at gravitational, centripetal, or subatomic fields, raw physical state mapping bypasses the absolute need for artificial guess math. The physics of localized phase rupture and violent pressure implosion spikes emerge totally naturally from the data, but only when you just let the SVD tensor map the raw Pascals directly. The structure of reality quite literally maps itself. To wrap all of this up, that Python script revealed an explosive, wildly unbiased truth about the hidden geometry of the universe. VCav emerges as the single, undeniable primary coupling channel, holding 99.10% of the total system variance. This proves, without a shadow of a doubt, that total kinetic agitation energy density utterly dominates the field. It acts exactly like a fluid where low-pressure voids violently collapse into pressure implosions. It is just a stunning, beautiful validation of raw physics over normalized statistics. Which leaves us with a truly mesmerizing thought to walk away with today. The data shows us, without any artificial scaling or statistical assumptions, that particle collisions act exactly like cavitation. But if subatomic particle tracks behave fundamentally like a cavitating fluid violently collapsing into pressure spikes, what is the actual invisible fluid of the universe that they are moving through? Now that is a profound question to ponder. Thank you so much for joining me on this explainer, and keep questioning the true nature of our reality.